You're welcome. In this video, we are going to talk about principles of drug action. Right. So targets for drug action. Targets for drug action. You must be knowing that when I taking drug or when drugs are taken in, these drugs need to bind to something before it can cause the pharmacological action that we need. So some drugs go into the body and they must bind to receptors. Some drugs are taken in and they need to act on certain enzymes. Some drugs are taken into the body and they're supposed to bind to carrier molecules. Some drugs are taken into the body and they are supposed to bind to ion channels. So we must be knowing that when drugs are taken in, they need to bind to certain targets before their pharmacological activity is induced. However, to every rule, there are exceptions. So there are other drugs too that do not need to bind to anything, and you will know them very soon. So this is something a drug will not work unless it is bound. Just as I said, and when I take in a drug and the drug doesn't bind to any of the things that I said, then the drug is not going to work. So some drugs need to bind to receptors because the intrinsic activity to bring out the pharmacological activity that I need. So drugs needs to bind to something, and you look at those targets very soon. However, since to every rule there are exceptions, it means that there are some other drugs too that do not need to bind to anything. They just need to be taken in and it breaks down and causes the pharmacological activity that we need. But most of the drugs needs to bind to certain targets, and we look at them very soon. So these are the exceptions. Please know this very well. These drugs here do not need to bind to anything. They just need to go into the body, break down, and bring out that kind of pharmacological activity that we need. So an exception here is one, osmotic diuretics. They are drugs that are taken in to help me urinate more. Why? Because maybe the kidney filters something, right? Some substances, and it doesn't need to be in the body. So I'll take in osmotic diuretics, it will help me to urinate more. So what the kidney filters, it will come out. Osmotic diuretics. It doesn't need to bind to any special target before it starts its pharmacological activity. Good. Now, we have something here called osmotic purgatives, like laxatives, that are used to treat constipation. It doesn't need to bind to anything. It just needs to go in there, break down, and start the pharmacological activity needed. Antacids. When the acidic content in my stomach is too much, I take in antacids. And antacids help to neutralize the stomach acidity, to bring the acidity of the stomach down. Antacids too do not need to bind to any target. They need to go there, break down, and cause the pharmacological activity needed. Again, heavy chelating agents. These drugs are used to remove heavy metals from the body. They are used to remove certain heavy metals from the body. It doesn't need to bind to any targets, cause any kind of physical activity. It is just taking in, breaks down, and causes the action needed. Targets for drug action. So if you look at the exceptions, that these ones, those drugs just said, cosmetic purgatives, diuretics, and all that, they do not need to bind to anything to cause any kind of metabolic activity. It should be taken in and just break down and cause the action. Now, we're saying some drugs do need targets. These are some of the targets that drugs should bind to. And the first one is enzymes. So some drugs need to work on enzymes or bind to enzymes. Some drugs too need to bind to carrier molecules. Okay, and we will get to know them soon. Some drugs need to bind to ion channels, and some too need to bind to what? Receptors. So whilst I'm saying that there are exceptions, some drugs don't need to bind to anything. There are some other drugs too that needs to bind to certain targets, and these are some of the targets. And this was RICE. So an acronym for you to remember is what? RICE. 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 So R is for receptors, I is ion channels, C is carrier molecules, E is enzymes. RICE. Now there are other targets too, aside the RICE. There is a drug called cortisone. Okay, this is used to treat gout and some kind of Behçet disease. Used to treat gout and Behçet disease. Now, this cortisone needs to bind to a protein called tubulin. Tubulin. Okay, yes. So that is the target for this drug. And another drug is cyclosporine or cyclosporine. And this drug is an immunosuppressive drug. You know what? It is used with other drugs to prevent the body from rejecting a transplant organ or transplanted organ. If I go for kidney transplant, my body will reject it. You get it? So what I can do is that I can suppress my immune system so that the body don't realize that as a foreign something, so that it rejects. So cyclosporine is used to reduce the immune system of humans. That is called immunosuppressive drug. When it reduces the immune system, the organ that have been transplanted cannot be rejected. And this special drug don't bind to the receptor. It doesn't bind to ion channel. It doesn't bind to carrier molecule. It doesn't bind to enzyme, but it binds to a specialized proteins called immunophilins. Purchasing to treat gout also binds to specialized proteins called tubulin. So we need to understand that here we are saying that targets for drug action. Some drugs work on enzymes, carrier molecules, ion channels, and receptors. But you must be knowing that these drugs do act on specialized proteins called tubulin. Cyclosporine acts on specialized one called immunophilins. Okay, and you should remember very well that cyclosporine is for immunophilins and cortisone is for tubulin. Don't confuse the two. So let me say targets. So when I ask you, give me an examples of drug targets. So you can tell me what? Receptors. You can tell me ion channels. You can tell me carrier molecules. You can tell me enzymes. You can tell me tubulin. And you can tell me immunophilins. But you must be knowing, not forgetting, there are some other drugs that do not need any targets, like the osmotic negatives, diuretics, antacids, and all that. Video. Now you're going with the first one, that is enzymes. So you must be knowing that many enzymes form useful drug targets. Yes, some of the enzymes, many of them forms a useful drug target. For instance, some of the drugs, when they are taking him, they are prodrugs. Okay, a prodrug is not really active. When you go into the body, enzymes work on that prodrug, break it down, and bring out the active drug. That active drug is going to cause that kind of pharmacological activated. Ɛduru na mɛfaeɛ no, ɛyɛ prodrug. Prodrug no kyerɛ sɛ, saa duro no ntumi nyɛ action biara, ɛnyɛ active. Sɛ ɛkɔ body no mu a, certain enzymes will work on it. Now breaking it down. Na afei ɛyi the active drug na ɛwɔ prodrug no mu afiri mu. That active drug no, ɛna ɛkɔkɔyɛ adwuma no akasakasa ma atɔme. So many enzymes form useful drug targets. So without the enzyme, many maduro no, sɛ duro no yɛ prodrug a mɛnom, body ma ɛnyɛ hwee. So many enzymes, the enzymes work on prodrugs and convert them into what? Active drug. So active drug no, ɛna ɛkɔ sɛ mɛyare. Now, often the drug mimics the natural substrate, acting as a competitive inhibitor of that enzyme. Now, I've made the first video. Go there and look at it. Substrates an enzyme and products, and you understand this statement. Often the drug mimics the natural substrate. Naturally, the enzyme that is in the body acts on certain substrates. Okay, the enzyme that is in the body naturally acts on a substrate in the body. When I'm taking the drug, okay, that enzyme, now that enzyme will confuse that one as the natural one and work on that too. So anything the enzyme is working on is called a substrate, and I've made a video on enzymes and substrates. You can check that one out and you really understand this concept. So when taking a drug, the drug is going to act as if it is a natural substrate in the body, and the enzyme will work on it. So this is, yes, an enzyme. Enzyme. Now, some drugs are taken in and it inhibits the enzymes from performing the normal reaction needed. So it means that the normal reaction will be inhibited. For instance, an enzyme called salivary amylase should act on what? Starch and convert it into, let me see, some other thing. Now, when this drug is taken, it binds to the enzyme and prevents the enzyme from acting on the starch to convert it to maltose, whatever. So at this point, the drug that is taken has inhibited the enzyme. So the normal action of the enzyme will be inhibited. That's the normal reaction was inhibited. So when the starch will be in the body, but it cannot be converted. Why? Because a drug has been taken in and can bind to that enzyme and stop its function. Now, false substrates. Now drugs go in there and they are false substrates. This is an enzyme. Okay, this is a false substrate. What that means is that, let's say this enzyme naturally works on something called dopa. And this enzyme, it works on something called dopa and convert it to dopamine. Dopamine. That's the true substrate that the enzymes works on. So this enzyme works on dopa to dopamine, right? Dopa to dopamine. But I can give you a drug. That drug is going to act as if it is the dopa. But it's not really dopa. That example of drug is alpha methyl dopa. Methyl dopa is not dopa. So, and the structure is the same thing as dopa. So that there's a methyl group attached. So the enzyme will think, this drug it looks like dopa, okay, then it will act on it. So instead of the enzyme working on dopa to get dopamine, the enzyme will work on a false substrate called the methyl dopa and get methyl dopamine. So instead of drug working on dopa to get dopamine, it works on the false substrate. Because that substrate is going to fool you. The enzyme will think it is the dopa, but it's not dopa, it is the methyl dopa. So the enzyme will work on the methyl dopa and bring out methyl dopamine. Meanwhile, we need dopa to be converted to dopamine. So at the end of the day, abnormal metabolite is produced. This is also an enzyme. It acts on a prodrug and bring out an active drug that I said earlier. In this prodrug, any active drug, right? But the enzyme will work on this prodrug and then break it down and give you an active drug. This active drug is going to give you that kind of pharmacological action you need. So this is a table talking about enzymes, inhibitor, and four substrates. Good. So you see the methyl dopa I'm talking about here. This one is dopa decarboxylase. This enzyme works on dopa, not methyl dopa. But there's a drug that's made, and methyl group has been attached to the dopa. So the enzyme will work on this methyl dopa and convert to methyl dopamine. Meanwhile, also the dopamine, methyl dopamine. Right. So know this table very well. Draw it somewhere, inhibitor and the four substrate. God being so good, we have only one methyl dopa here, right? So know that. And that one is for the dopa decarboxylase. Know these ones too. So just know the table of head. Before you can appreciate this, you need to really know what the drugs are going to do. Before you can have it off head. Other than that, you need to do a table and just do it from time to time. Because you can be given the table for it to fill in. So acetylcholinesterase is an enzyme that breaks acetylcholine to acetate and choline. Now, to inhibit this enzyme, there's a drug called neostigmine or pyridostigmine or physostigmine. These drugs are going to arrest acetylcholinesterase and prevent it from breaking down acetylcholine. So this drug becomes an inhibitor. And dampezel is also such. Aspirin is used to block the cyclooxygenase. So that one becomes an inhibitor. So just do the table and then know where each of them belongs to. Ion channel. You see, I've already talked about receptors in the first video. So please, if you haven't watched the first video, you need to go and watch it before you get a very good and broad understanding here. Now, protein molecules that span the cell membrane. I told you ion channels are 4 to 5 parts receptors. You're going to understand the concept when you watch the first video. Now, protein molecules that span the cell membrane. Why? Because it is 4 to 5 parts receptor. Now, can switch between open and closed states. So these ion channels can close or open. That is when a ligand binds to it. I explained ligand in the first video. Anything that binds to a receptor is called a ligand. So drugs can bind to receptors. They are called ligands. Hormones can bind to receptors. They are called ligands. Transmitters can bind to receptors. They are called ligands. Other toxic substances can bind to receptors and they are called ligands. So the channel can open or close when the ligand binds to it. Now, allow the controlled entry or exit of specific ions across the cell membrane in their open states. So when the ion channels are open, not any ion can go through. They are very selective, they are very specific with a special type of ions that should go through them. Now, ion channels are highly selective for the ions that they control, as I said. So the ion channels are selective. Not every ion can go through. They have specialized ions that needs to go through them. And the ligand binds to it. So this outside the cell, the cellular fluid inside the cell, cytosol. This is the cell membrane. Okay, this is the ion channel. Ion channels. Here it is closed, and here it is open. Why? Because a ligand binds to it. And ligand binds to it, it's open ions to go in there and causes the intrinsic activity that we need. So ion channels are gated. They are all gated. They have particular triggers that allow for their opening. That's why I said that here, since it is open, since it's closed, it can be open and something binds to it. A ligand binds to it. So we have ligand gated, voltage gated, meaning that this one they are gated. But when the introduction of ligand to open, okay, so this is a ion channel, but some drugs go there and block the ion channel. Some drugs go in there and block the ion channel from opening. So for instance, if this ion channel is supposed to be opened by a ligand called maybe norepinephrine, let me say acetylcholine, I can give you a drug that is going to bind to the ion channel. So that even if acetylcholine binds, because I'm giving you a block, the ligand will bind, but it cannot open because the drug has blocked the channel. So here permeation is what is blocked and ions cannot enter. We also have modulators. This drug is taken in there and it modulates how well the ion channel should open, how it should open, the bigger, medium, something. So increase or decrease opening probability. So some drugs go there and block the ion channels. Some drugs also go in there and modulate how well they should increase or decrease opening. So this is also a table. You need to know this table of it. Voltage gated sodium channel. A blocker here is local anesthetic. And you must be knowing that sodium are involved in the action potential. The influx of sodium involving active potential. And with the pain, when there's active potential, that is when you're going to observe the pain. But when I give you something to block the sodium channel, what that means is that there will be no active potential and therefore there will be no pain. That is why there's a blocker called anesthetics. They are used to block this kind of sodium channels. We also have modulators, very. So you have to draw the table and make sure you know where each of them belongs to, blocker and modulator, and its respective ion channel. Right. So I've talked about gene protein coupled receptors already. Gene protein coupled receptors in the first video. So for you to understand this diagram very well, please go to the first video and watch it, where I talked about receptors and all that. Now, this is gene protein coupled receptor, this one, and it's acted upon by a ligand. We have gene protein coupled receptor ligands come and act on the gene protein coupled receptors. Now, here, they will come down and then activate second messengers. I've explained all this in the first video. And second messengers will also go and activate protein kinase A or protein kinase C. And they are going to add phosphate groups channel for the channel to open so that ions will go inside, come inside, you understand? And then cause the cellular effect that we need. So to understand this, go to the first video and watch it. Now we also have channel block. We're taking drugs, it comes to the ion channel and it blocks the ion channel. So these are channel block, the same thing here. So look at anesthetics, then all these drugs go here and block the ion channel from opening. So the ions do not will come into the cell to cause that kind of cellular effect. Now, carriers responsible for transportation of polar molecules across lipid membranes. There are some molecules that are polar. In order for you to cross a membrane, you need to be lipid soluble. However, there are some molecules that are polar, so they cannot cross the same membrane. So they need carriers, carry them into the cell. They are often specific for a particular molecules. So the carriers you have in the body, they are very specific. It doesn't pick any molecule into the cell. It chooses the molecule, it moves into the cell, it carries into the cell. Now, these sites can also be targets for drugs whose effect is generally block the transporter. So normally, let's say we have carrier. Let's go here. So this all that. This is a carrier. So it normally for normal transport, it carried the molecules here. The molecule is coming here, and here it binds. Then it turns upside down and bring the molecule into the cell. It is now in the cell, and it's going to cause the activity needed. We can some other drugs here can also when I can give you a drug, that drug will come and bind to this. Therefore, the substance, the molecule that needs to be carried out into the system to cause that kind of activity will be blocked. So some drugs are carrier inhibitors. The drug is taken in and it inhibits the carrier. So if there's a substance in my body that always needs to be carried into cells by a transporter, I can take in a drug and that drug is going to block that carrier and prevent that carrier molecule from transporting that kind of indigenous substance into the cell that I need. So here it comes here and the drug fixes here, therefore block this ion channel, and block this carrier molecule from getting this kind of molecule into the cell. Or it can also bind, it will allow the molecule to bind. But the inhibitor that the drug I'm taking to will bind to this one and prevent the molecule from coming into the cell. Here so means transport is blocked. False substrates. As I defined it earlier, okay, it also leads to abnormal compound accumulated. So the false substrate is not a true substrate. It's not a true something the parent molecule works on. It is coming as if it is this kind of substance here that the molecule the carrier molecule always carry into the cell. But for you know, that drug is acting as if it is that molecule, but it's not that molecule. So at the end of the day, the carrier will carry this molecule into the cell. But since it's not the true molecule, it's going to result in an abnormal compound accumulated. So here to know the carriers and inhibitors. So go to the table and know it offhand. You understand? Good. So for instance, noradrenaline is inhibited by cocaine. And cocaine, it will get more of norepinephrine into the synaptic cleft. Okay, and the reuptake of noradrenaline or norepinephrine is ceased. So I have more norepinephrine in there. And the moment I have norepinephrine in the synaptic cleft, that means that it's going to keep me excited. It's going to give me hypertension. So that is why those who take cocaine, they experience excitement. When I have more of norepinephrine release, I get excited. And also my hypertension too goes up. So no adrenaline uptake inhibited by cocaine. So at least I have more of norepinephrine not taken back into the presynaptic neuron. So draw the table and then know the drugs, the carriers and the various inhibitors. Or you can search for the drugs and know what they do before you can really have it off head. Now receptors, I've explained receptors as I said in the first video. Now I explain the concept of agonist drug and antagonist drug. Now here, agonist drug, okay, this drug binds to the agonist and cause effect. So at the end of the day, they bind to the receptor and then open the ion channel like a ligand. I told you, and it binds here, a ligand binds to receptors. So this one, if it's agonist, it will bind and cause activity by opening ion channels, ions to go inside the cell to cause activity, or by activating certain enzymes to cause certain activity, or by modulating certain channels, okay, and all that. So the point here is that if the receptor is here, and what is coming to bind it, the ligand is agonist. When it binds, it should cause an effect or intrinsic activity. But antagonist drugs, when they are taken in, they bind to it only, but it doesn't cause any effect. So I've explained the concept of agonist drug, antagonist drug, partial agonist, partial antagonist in a different video. So go there and look at that video and come back here and you understand the concept very well. Receptors. A cellular macromolecule. Yes. At first, we were saying receptors are proteins, but we can't say that anymore. Why? Because DNA is not a protein. So at first, we define receptors as proteins, but I realize that no. If we should say proteins, that means that we are taking DNA out. But we have some anti-cancer drugs that bind to DNA and cause cellular effect. So because of that, and we say receptors are macromolecules. So a cellular macromolecule, a complex of macromolecule, or an assembly of macromolecules that is concerned directly and specifically in chemical signaling between and within cells. And for a receptor, you have two functional domains. A receptor should have a point where ligand binds to it, and it should have an effector domain to release intrinsic activity. So a receptor should have what? A ligand binding domain and should have an effector domain. To understand this very well, go back to receptors. Anything that binds to a receptor is called a ligand. An example of ligand is drugs, neurotransmitters, hormones, soil substance. These are all ligands and they bind to receptors. Now, a signal transducing protein. So a combination of hormone, neurotransmitter, drug, intracellular messenger with its receptor initiates a change in function. Yes, so for me to cause a change in cell function, that means that a ligand must first bind to receptors on the cell. When it binds to the receptor should activate and cause intrinsic activity. That's why plasma proteins are not receptors, Why? Because drugs can bind to plasma proteins, but they do not cause any kind of intrinsic activity. So for a receptor, you have a ligand bind domain and effector domain. But plasma proteins are having a ligand bind domain, but it has no effector domain. So they are not receptors, even though drugs bind to them. So drugs need to bind to receptor, activate the receptor to activate the cell, cause intrinsic activity, or there will be change in what you're looking for. Most, though not all, receptors are membrane spanning proteins. Yes, they are membrane spanning. As I said, for ion channels, there are 4 to 5 parts receptors. They span the membrane 4 to 5 times. We have a specialized receptor called serpentine receptor or 7 parts receptor or protein couple receptor. They span the membrane 7 times. Receptor video, and it's what I'm talking about. We also have 12 parts receptor. They span the membrane about 12 times, going up and down 12 times before they cause intrinsic activity. So receptors membrane, they are mostly membrane spanning proteins. Now, like I said, that's the trade name, and the generic name or the trade name, sorry, the official name is what? Chlorpromazine. The trade name is Lagacel. Now, it's a kind of antipsychotic drug, and it's used in what? Schizophrenia. What is schizophrenia? It is a serious mental disorder. Schizophrenia is a serious mental disorder. And do you know what this drug is going to do? This drug, like I said, is going to act by antagonizing dopamine due to receptors. This drug is going to antagonize dopamine due to receptors. So they go and serve as antagonists at the following receptor sites. So like I said, comes here to histamine H1 receptors and bind to it. When it binds, it will not cause any kind of action. So it's working as what? As an antagonist. So it binds to histamine H1 receptors and acts as what? Antagonist. It also binds to alpha adrenergic receptors and acts as what? Antagonist. It also binds to bradykinin receptors and act as antagonists. It also binds to muscarinic receptors and act as antagonists. And by way of doing that, when it antagonize one, it is trying to antagonize the dopamine receptors, and therefore it is used to treat antipsychotic. It is used to treat this kind of schizophrenia, which is a serious mental disorder. Now, this of receptors, the 3S. Receptors are very sensitive. A receptor should be very selective. A receptor should be very specific. What do I mean by a receptor should be very sensitive? Now, it should mark effects at extremely low concentration. So I'm a receptor, even if something that stimulates me is at low level, it gives some kind of effect. With a little amount of ligand present, I should detect it and cause that kind of cellular effect. So it should mark effect at extremely low concentration, even though the ligand that is coming low enough. But because I'm a receptor, I am very sensitive. Even the smallest agonist present will bind to me and I'll cause that kind of activity needed. They are very selective, very selective. Now, display a preference for one optical isomer of drug. For example, levonoradrenaline is 100 times more potent than dextronoradrenaline. They are all noradrenaline, but for the levo, the chemical structure is levo means left, and then dextro means to right. So looking at the chemical structure of it, the levo structure was moving to left, and then for dextro is to right. Just a change, a slight change, a slight conformational change in the drug the receptor will not accept. So they are very selective. So that's something that, for example, levonoradrenaline is 100 times more potent than dextro. They are all adrenaline, but just that the levo is to left, dextro is to right. But say there be, or no, we are left in one or best two. They are more potent to not levonoradrenaline than dextronoradrenaline. That means they are very selective. The same drug, but one chemical structure, every left, but what they have right, see there be, if I left them, they are very selective. Sometimes only one isomer or appreciably bind to a receptor, like dextromethorphan. You have levomethotrexate. See there be chemical structure, but when left, but right, but yeah, right and one other bind to the same drug. So it tells how selective they are. Specificity, very specific. Responses of cells of any given type to agonists acting on the same set of receptors is always of the same type. So the response of this kind of receptor to agonist, they choose special agonists they need to bind to. The response of cells of any given type of to agonists acting on the same set of receptors is always on the same type. So the same agonist will work on the same receptors for that kind of receptor. We have different agonists acting on different receptor that is not designed for. And specificity is what? Reciprocal. So we have specific agonists should bind to specific receptors. And if I'm a specific receptor, I should bind to a specific agonist required. The receptors here to the same thing. Make sure you know the drugs that way. You can only know it offhand, as I said, only if you know all the drugs are doing. If not, draw a table and know it. Now, nicotinic receptor. Okay, nicotine can stimulate this kind of nicotinic receptor. But the drugs here are going to antagonize it. It will bind to the receptor, it will not cause any activity. Agonist, nicotine will bind to nicotine and cause intrinsic activity required. Antagonists will bind, but it will not cause any intrinsic activity. So know various receptors and know the various agonists working on them and know the various antagonists working on them. You know this table because it can also be in the exam. Now, types of receptors. Now, if you want to watch the video on receptors, this is very something easy to understand. So you have four superfamilies: type 1, type 2, type 3, type 4. Type 1 is channel-linked receptors and they're ligand-gated. Why? Because this channel, these gates, the gate of the channel will open for ions to come inside when ligands bind to it. So they are ligand-gated. They are ligand-operated. Ligands will operate on them before the channel will open. The gates of the channel will open. The gate of the ion will open for ions to come inside. So that's one type. You have G protein coupled receptors, and they bind what G proteins. And G proteins are also called what? Serpentine receptors, or they look like a snake. And there are 7 passed receptors because they span the membrane 7 times. You also have kinase linked receptors, and these receptors actually add phosphate groups. Kinases, they phosphorylate, they add phosphate groups, right, to cause certain activity needed. Type 4, receptors that regulate gene transcription, like nuclear receptors. They are also in the nucleus that I said. So you can understand this very well when you watch the videos on receptors. Now, ligand, so these are the receptors types. So we're looking at how they function, how they are operated, cause cellular effects. Cellular effects. For instance, if I say I've taken a drug, at the end of the day, cellular effects in some anatomy. Nti ɛbaa ne sɛn ɛna do na mefaeɛ no ekoa mabɛnya the cellular effect that I need. That's what we are looking at. So all of them will result in what? Cellular effects or the changes, the intrinsic activity required. So let's start with the first one, ligand-gated ion channels. And they are also called ionotropic receptors. So don't forget ion, ligand-gated ion channels. They are also called what? Ionotropic receptors. You know what is happening? The ligand will come and bind to the receptor, the ion channel. Okay, so ligand is this one. It's come and bind to the receptor. When it binds, it opens the channel. Ions come inside, and that is going to cause hyperpolarization or depolarization. And by there, when the ions come inside, they are going to cause the cellular effects that we need. The time scale is milliseconds. So under milliseconds, so milliseconds it is operated. Milliseconds. Example of it is what? Nicotinic receptor. We have two types. We have acetylcholine receptors. Acetylcholine can bind to nicotinic receptor. It can also bind to muscarinic receptor. But nicotinic receptor is what? It's a ligand-gated ion. It's an ion channel. So when acetylcholine binds to nicotinic receptor, when it binds, it opens the nicotine in for the nicotinic receptor, the ion channel. It opens it for ions to come inside. So a critical example of ligand-gated ion channels was nicotinic receptors. That is that. Now let's go to gene protein couple receptors. And other name is what? Metabotropic receptors or 7-pass receptors or entire receptor. How do they work? A ligand will come here and bind to the receptor, okay, and to stimulate the gene protein. When it stimulates, and then certain enzyme will work on second messengers. And I've explained this in the first video. Will work on the second messengers. Example of second messengers: IP3, DAG, AMP, and even calcium. They are all second messengers. When you go there, you understand very well. Now, when second messengers are activated, they also cause protein phosphorylation. And here, they are going to cause cellular effects that we need. They can also activate ion channels. So when a ligand comes here, it binds the receptor, activates a gene protein, and then it goes there to activate certain ion channels, not ion channels, sorry, still the gene protein. It's allowing certain ions to come inside, okay, and releases calcium. For instance, this ion here is not ion channel. This thing here is ion channels actually not as a receptor, but they are ion channels on endoplasmic reticulum in the cell. Endoplasmic reticulum is having too much calcium. But for me to get the effect that I need calcium in the cell, the cytosol, not in the endoplasmic reticulum. So the gene protein is going to bind to this kind of channel in the endoplasmic reticulum to release more of the calcium into the cell. We call that kind of cellular effect. Also happens in seconds. An example of what is muscarinic receptor. I told you that acetylcholine can bind to either nicotinic or muscarinic receptor. But for nicotinic receptor, it is ion channel. But for muscarinic, it is a gene protein couple receptor. Now let's go to kinase link receptors. You know what? The ligand will come and bind to this kind of receptor, the kinase link receptor. Okay, I told the when you have kinase, they add phosphate groups. They cause phosphorylation. So here they are going to cause protein phosphorylation. Okay, and that is going to cause a gene transcription. And this gene transcription is going to lead to protein synthesis. And these proteins that are being synthesized are going to cause cellular effects. It happens in hours. An example here is the cytokine receptors. Right. So nuclear receptors, what it's doing is that now this is a ligand, and ligands are what? First messengers. They come here, you see here, they come to nucleus. That's why I told you that not all receptors are in cell membranes. Some of them are even in the nucleus. So this ligand here comes into the nucleus and binds to a receptor in the nucleus. You realize that they are on cell membranes. but this receptor is in the nucleus. So the ligand comes here and binds to the receptor and causes a gene transcription, causing mRNA to cause protein synthesis. And this protein synthesis is going to cause of cellular effects. This happens in hours. An example of this receptor is called estrogen receptor. So here, protein synthesis are involved, gene transcription involved to cause that kind of cellular effect. So know the hours they operate and know the examples of channels and know other names of the receptors and know the mechanism, just as explained. Right. Now, the general structure here, it is talking about the receptor, the bind domain, and the effector domain. Okay. Ligand-gated ion channel. I told you this is the ion channel. When you look at this way, you might think that, oh, yeah, this is space that ions go in and come inside. But look at it. It is membrane spanning. That's why I explained the video that ion channels or ligand-gated ion channels have 4 to 5 parts receptor. Yeah, they are span the membrane 4 to 5 times. Get it? 4 to 5 times here, and mostly 4 to 5 times. So ion channels are receptors, and they are also called 4 to 5 parts receptor because they are spanning membrane 4 to 5 times. So when the ligand binds to it, it opens up for ions to come in this way. Now, the 4 main receptor types. Let's look at some things between them. Their location. Ligand-gated ion channels. Oh, they are on membranes. They are membranes. I explained in the other video, and here too, you can see that they are on membranes. Okay. Now, receptors, they are also on membrane, cell membrane. They are also on cell membrane. Receptor kinases, they are also on membranes. Nuclear receptors, they are found inside the cell. I told you that not all receptors are on the cell membrane. Some are in the cell. So for nuclear receptors, they are inside the cell. Now, effector, I told you that for every receptor, it should have a ligand bind domain and you have an effector domain. So if you know what the video, please go there and watch the video. This is the effector for ligand gated is that ion channel. So when ligand binds to it, the ion channel will open. So the opening of the ion channel to allow ions to go through is going to cause that kind of intrinsic activity. So the effector here is ion channel. To understand it very well, go to the video on receptors. Now, gene protein effector, they are coupled with enzymes. Okay? Gene proteins are coupled with enzymes. So here, their effector is the channel or the enzyme. Now, receptor kinases effector is the protein kinases. We have protein kinase PKC, PKE, protein kinase A. These are the effector. For nuclear receptors, the effector is what? Gene transcription. Now let's go to coupling. Ion channels, are they coupled? No, they're not coupled. Ligand binds with and opens for ions to come inside on its own, just like that. But gene protein coupled receptor, they are coupled with gene protein. So this receptor is attached to a particular protein, and this protein is what? A gene protein. So if I'm talking about coupling of gene protein coupled receptors, then the coupling is what? A gene protein. So here, because there is no coupling, it is direct. Receptor kinases, they are also direct because it is not attached to anything, it is direct. Now, nuclear receptors, they act via DNA. They act via DNA, so they are the coupling. Example of ligand-gated is the nicotinic acetylcholine receptor. As I said earlier, GABA, all examples. Gene proteins, muscarinic receptors are gene proteins. Are gene protein coupled receptors, and albino receptors are also gene protein coupled receptors. Now, for example of receptor kinases, insulin, growth factors, cytokines, receptors. These are all examples of receptor kinases. Just know them. Example of nuclear receptors are steroid receptors. Steroid receptors are lipid soluble. That's why they're able to cross the cell membrane and come into the nucleus and activate those receptors. So you have steroid receptors. Now the structure for ligand-gated ion channel, they are what? Oligomeric. And you must be knowing that when I say oligomeric, you have more than one subunit. Gene protein coupled receptors are monomeric, or it can be oligomeric, having subunits. For receptor kinases, they are single transmembrane helix. They are single transmembrane helix. Now, nuclear receptors are monomeric. Why? Because they have single peptide chain. Now, signal transduction. Signal transduction is the process by which extracellular inputs like a drug, receptor interaction, they interact the affinity between drug and receptor. That is going to lead lead to intracellular messages that modulate cellular physiology. So signal transduction, okay, is that when a ligand comes to bind to a receptor, that of interaction should activate and cause a change in the cell. That is what we're talking about. So within the cell signal transduction, I am a ligand. A ligand will come and bind to a receptor. When it binds to a receptor, it is going to bring out intracellular signaling proteins, specialized proteins that is going to release them. Okay, so it's going to bring about certain proteins, stimulate certain proteins, and if that protein that is brought about as a result of the ligand binding to a receptor, if it is cytoskeletal protein that is produced or that is activated, it is going to alter cell shape or movement. So cytoskeletal proteins are for shape and movement. So if a signal, or if let's say a ligand binds to a receptor and then they activate certain proteins to cause certain proteins to release, okay, that means that if it is cytoskeletal protein, it is going to alter cell or cell shape or movement. If that protein is a gene regulatory protein, then it is going to alter gene expression. If that protein is a metabolic enzyme, then it is going to alter metabolism. So you must be knowing that for intracellular signal transduction, a ligand should bind to a receptor, and the receptor at the end of the day should cause signaling of intracellular proteins. And these are going to stimulate certain proteins to cause certain actions in the body. So this is signal transduction by steroids. This is the steroid hormone. It is able to pass through the membrane, but it is lipid soluble. So when it comes to it binds to the receptor. Okay, so here it binds to the receptor. Is a receptor. It's a steroid hormone. When it binds in the nucleus, I'll have the hormone receptor complex. The moment I have a hormone and a receptor coming together, I'll call that a hormone receptor complex. That is going to cause a gene transcription on DNA, right? To release messenger RNA, to release new proteins, and the new proteins are going to cause the actions that I need. That's why here I was saying that these proteins are going to cause some changes in the cells that are needed. So still hormones will bind to receptor and I'll have what? Hormone receptor complex. It will act on DNA and causes gene transcription. Messenger RNA will lead to new protein synthesis. And if the new protein that is synthesized is a cytoskeletal protein, then you should know that I'm going to alter cell shape or movement. If the new protein is a gene regulatory protein, it's going to alter gene expression. If that new protein that is synthesized its metabolic enzyme is going to alter metabolism. Now we have gene protein subunits. I've explained this one when I'm talking about receptors. So if you've not looked at receptors, please go there and look at receptors very well. We have gene stimulatory, gene inhibitory, gene kill, and gene load. These are subunits. These are alpha subunits of the gene protein. So if it is gene S, it's going to stimulate. Gene S stimulates. Gene S stimulatory means gene stimulatory. It's going to stimulate an enzyme to release more cyclic AMP. And the more cyclic AMP I have, it is going to cause the cellular effect that I need. Gene inhibitory is going to inhibit adenylate cyclase. So I'll have little or no cyclic AMP producing. So I wouldn't have that kind of cellular effect. Gene kill activate phospholipase C, an enzyme, okay, and then break down lipids on cell membranes to IP3, inositol triphosphate, and diacylglycerol. Okay, so because it activates phospholipase C will also bring about more inositol triphosphate and diacylglycerol. So you should note this one, that this is also activated by pyruvate toxin, which blocks GTP's activity, that's preventing inactivation. And this one, so the gene will also blocked by peptides toxin. And for gene inhibitory, it is blocked by peptides of toxin. Okay, if it prevents solution of alpha beta gamma subcomplex. And if it doesn't dissociate, always alpha needs to dissociate from the beta gamma subunit before it can be activated. So if it cannot dissociate, that means that it has been inhibited. So it will not cause the cellular effect that I need. Yes, so gene protein coupled receptor signaling, example is let me say epinephrine. So this is a ligand. A ligand should come and bind to receptor. Okay. Now this ligand that is going to bind to a receptor is called the first messenger. So this is a signal molecule. An example is epinephrine. Okay. So epinephrine that's going to bind a ligand. And ligands are mostly first messengers. They bind to receptor. I've explained this in receptors. So please go there and have a broad general idea about what is stimulate the receptor, and this receptor that is stimulated by the first messenger or by the ligand is going to stimulate gene protein. But the gene protein is GDP. The moment a ligand binds to a receptor, then the gene protein converts from GDP to GTP. And this GTP gene protein is going to stimulate an enzyme called adenylate cyclase. I've explained all this with beautiful diagrams in the video. Adenylate cyclase is going to convert ATP to cyclic AMP, and this is going to activate protein kinase A. And protein kinase A is going to cause phosphorylation, cause the cellular effect that I need. So I told you that second messengers, cyclic AMP is a second messenger. IP3 is a second messenger as inositol triphosphate. That's a glycerol, DAG, is also a second messenger. Calcium is also a second messenger because they perform certain actions. So the first messenger is always the ligand that is coming to bind. Okay, good. So cyclic AMP as a second messenger, effect of epinephrine on liver cells. So the protein kinase A that will be activated by the second messenger, cyclic AMP. The protein kinase A is going to actually cause phosphorylation. So let me go over it again. So here, first messenger, the receptor, okay. So the ligand will bind, the ligand, the first messenger, it will bind to what? Receptor, and the receptor will stimulate a gene protein. And I said that in the inactive form, it is GDP, not GTP. But the moment the ligand binds to receptor, it's converted from GDP to GTP. And this G protein is going to activate adenylate cyclase. Adenylate cyclase is going to convert ATP in the cell to cyclic AMP. Cyclic AMP, second messenger. It is going to activate protein kinase A. And protein kinase A is going to release phosphate groups to phosphorylate to cause the intracellular activity needed. So that is it. I told you that in the cell, in the video, that endoplasmic reticulum is rich in calcium. We need the calcium to in the cell here, the cytosol, to cause the cellular response that we need. So how can calcium come here and cause the action that we need? So before they can come here, it's phosphorylated. IP3 should come and bind to the calcium channel, and it binds it to open. The more calcium will come into the cell. So let's start again. So how does it start? First, the first messenger, the ligand, comes here and binds to the gene protein coupled receptor. And when it binds, it will activate the G protein. And I'm saying that in the inactive form, it is GDP, but the active form is what? GTP. And it becomes GTP only when the ligand binds the receptor. Then it becomes a GTP. So a ligand binds, first molecule that the ligand binds the receptor, and this receptor will activate the G protein. A G protein will activate phospholipase C. Phospholipase C will go to the cell membrane, the lipids over there, and break it down to DAG and IP3. IP3. The IP3, that's inositol triphosphate. This one will come to the calcium channel on the endoplasmic reticulum and then open the channel for more calcium to come inside. So calcium here, second messenger, and that is going to cause that kind of cellular response that we need. So it is called IP3 gated calcium channel. Calcium channel in the cell that is going to open when I have IP3. When I can have IP3, that's when all these processes goes by. The same thing to happen here. This is a first molecule, first messenger. It binds to tyrosine kinase receptor. And I told you that for tyrosine kinase, they phosphorylate. So they're going to phosphorylate the phospholipase C. And this is going to break down lipids on the cell membrane to IP3 and DHA. And the DHA didn't come. And the IP3 will come to the cell and then open the cell for calcium to come into the cell and cause the activity we need, cellular response. So this is control of cellular effector system. Okay. So I have receptors, I have gene proteins. So receptors will activate gene proteins. Okay. Receptor will activate when ligand binds the receptor will go to activate gene proteins. And gene proteins can either activate adenylate cyclase or activate phospholipase C. Phospholipase C will go to cell membrane and break the cell membrane, the lipids on cell membrane down towards IP3 and DAG. And IP3 is going to bind the calcium channel and release more calcium. And the DAG, that diacylglycerol, is going to cause phosphorylation. Here can lead to arachidonic acid, and then that's an eicosanoid, and it can be released as local hormones. Adenylate cyclase or activate cyclic AMP. Cyclic AMP or activate protein kinase A, and that's going to phosphorylate certain proteins and enzymes. Here, guanine cyclase, so these are all enzymes. Guanine cyclase, having the name ACE, they're all enzymes. Guanine cyclase going to activate cyclic GMP and to activate PKG, protein kinase gene. So here they activate protein kinases. These protein kinases are going to add phosphate group to cause the action we need. You understand? So here, if it is phospholipase C, the GAG is going to activate a kinase called protein kinase C. Phospholipase C bring DAG and it activates protein kinase C. You understand? Here, adenylate cyclase release stimulate cyclic AMP and then to go and activate protein kinase A. Adenylate A, protein kinase A. Guanine cyclase activates CGMP when activates protein kinase gene. Guanine. So all these things here that are here are the second messengers. Okay, and these are protein kinases. And the names of the kinases is PKG belongs to guanine. Protein kinase A, adenylate. protein kinase C by phospholipase C, and it's going to cause ion channels to open and cause phosphorylations and other things we can cause that kind of action we need. Now you should be knowing that at this juncture we've talked about the drugs and the target they should bind to, but you should not forget that we have some receptors, okay, some drugs that do not need any receptor to act. They do not need any receptor. They need to take it in, break down, and start their actions. They don't need to bind to any receptor. They don't need to bind to any enzyme, no carrier molecule, no ion channels. They need to take it in, break down, and start their action. And these are examples. Osmotic effect, like diuretics, and then antacids, and then this kind of heavy chelating agents, and then 5-fluorouracil and penicillins. These drugs don't need to bind to receptors or any targets. So to every rule, there are exceptions. So in this lecture video, we are saying that drugs should bind to receptors. They should bind to targets, but you should be knowing that there are exceptions. There are some drugs that do not bind to any. I know this video will be very helpful. Thank you very much. We look forward to the next video. Thank you.